Hey guys, welcome. Yeah, so I already made 5 videos on the 5 most important and basic Maclaurin series expansions. And those are for the functions e to the x, sine x, cosine x, arctan or inverse tan x, and then the natural log of 1 plus x. Now, for e to the x and sine x, we use the definition of the Maclaurin series. For the others of those 5 important ones, specifically cosine, arctan, and then natural log of 1 plus x, we used derivatives and then integral and integral in order, right? So you see already from having seen my video on the Maclaurin series for cosine x and for arctan x and for the natural log of 1 plus x, that Maclaurin series behave well under differentiation and integration. But that's not all you can do. You can multiply 2 Maclaurin series and so on. So in this example 1, and at least 2 more examples, what I'm going to show you is how to do precisely that, which is instead of reinventing the wheel and using the definition of the Maclaurin series, for some complicated functions like this one, it's better if you just use the 5 fundamental Maclaurin series that you know, and then modify them to make Maclaurin series for functions like this one. So it's better to start with the 5 important functions and their Maclaurin expansion, and I've already said which 5, and then to modify them to make Maclaurin series for, say, this function. So here, clearly, the 2 most important Maclaurin series that we need to know are for e to the x, and then in a little bit for cosine x. Now, starting with the Maclaurin series for e to the x, we can get to the Maclaurin series for e to the 3x very easily, and this way, yeah? And now we can, I suppose, simplify this a little bit more, and simplifying it look like that. All right. Now, similarly, starting with the cosine Maclaurin series, we can get the cosine 2 root x Maclaurin series like this. First, in place of x and cosine, we put 2 root x, and so that's here and so on. And now we simplify, and the simplifying here is a bit more work, but it's okay. Right, so first here, 2 root x to the 2n power means 2 to the 2n power, and then root x means x to the 1/2, so x to the 1/2 to the 2n. But x to the 1/2 to the 2n is like x to the 1/2 squared to the n, so that's just x to the n. And then 2 to the 2n is like 2 squared to the n, and so that's 4 to the n. Yeah? Okay, cool. So not too bad. And yeah. Now, where to from here is the question. Well, if we show the simplified version of the term by term of the cosine 2 root x Maclaurin series, it'll look like this. Now, we've got the cosine 2 root x Maclaurin series. We've got the e to the 3x Maclaurin series right here in their most simplified form. So how are we going to make the Maclaurin series for e to the 3x times cosine 2 root x? Well, multiply this by this, right? And that's how we're going to do it. Now, let's write a reminder of what the cosine 2 root x Maclaurin series is, because we definitely need space. I'm going to have to get rid of the one written down here at the bottom. Yeah? All right. Cool. So, there and there. And as I said, what we're going to do is take e to the 3x Maclaurin series right here, term by term, and then cosine 2 root x Maclaurin series right here, term by term, and multiply them. And when we do, this is what it's going to look like. All right, now, how do we do this? Because we're multiplying 2 infinite polynomials. Well, it's not so bad. So here's what we could do. We could first take this one and multiply to all of this, right? And then we could take the 3x and multiply to all of this. And by all of this, I mean the Maclaurin series for cosine 2 root x. And then take this guy here, the third term in the expansion of e to the 3x, and multiply to all of this, right? And so we could do it like that. And that's basically the distributive property, so I didn't invent anything new. All right, so that'll look like this. And of course, I need to have plus ... out here too, because the next thing we would have done is we would have taken the 4th term and the expansion of e to the 3x, and we would have multiplied it to the whole cosine 2 root x Maclaurin series and continue in that fashion. But I figured you caught on to that. Yeah. Okay. So, then where to next? Well, distributing this one here has no impact, so we're just going to get this guy here. Distributing the 3x to this infinite polynomial here is going to have an impact. First, this one is going to turn into a 3x, and this guy is going to be 3x times negative 4x over 2 factorial, and so on. You get it. And similarly, distributing this guy here will have an impact, and so on. Yeah? Okay, so that would mean like this, right? If we first distribute, as I said, it will look like this. And after distributing, I've highlighted all of the like terms. So the terms involving the same x power, right? I've highlighted them. So if you put them together, it'd look like this. That is, if you put like terms together next to each other, it'd look like this. And then from here, you've got more simplifying to do. Like, for example, minus 4x over 2 factorial, that's just minus 2x because, well, 2 factorial is 2, 4 over 2 is 2, and so you've got minus 2x. And then minus 2x plus 3x is going to become just an x. So really, the simplified version of the Maclaurin series for this here, e to the 3x times cosine 2 root x, is going to start with 1 and then plus x and so on. But I didn't want to bother with the simplifying work the rest of the way because, well, I've enjoyed making this video, and I think it stopped being fun if I did like simplifying algebra and like fractions and stuff. So this is it for me. I hope you enjoyed this, and keep watching. Take care.